Now can I hear myself? Well, there's a lot of lag, so I have to wait for my test device to catch up. Did I turn the line down too much? No, it's not. I don't think the stream is quite working. There. Oh, now I hear something. Alright, I plan to start in just a few minutes. I'll try to respond to questions that people ask in the chat or on the Slack channel. Do I get my audio back now? Yes. Okay, I turned off my desk fan, but there still seems to be a bunch of noise. So I suspect that we're just going to have to live with that. Does the audio volume seem good to people? It looks like it should be good on the VU meter. I'm not going to try to continuously monitor it. Just kicking something I didn't want to be. Welcome to Tech Lancaster, July 2020. We had a change of speaker again. That seems to be the pattern these last 5 months. The scheduled speaker had a family emergency to go deal with. So I'm filling in again. Not the only person who's filled in, but and tonight we will be discussing designing Crapduino, a quick introduction to Kicad. Just a few announcements first. I'd like to call attention to the Tech Lancaster Slack channel. If you're not already in that, then that's a pretty good place to find out about events or jobs or other things that you might want to know about. You can get an invitation by sending me your email in a chat or private chat during this live stream, or you can go to http://amishtech.slash.com. I also would like to call out some other meetups that have still been continuing during the COVID-19 crisis. The first is Lancaster AI. Their next meeting is July 28th at 6:30 p.m. See their website, lancasterai.com, for their streaming details. And then also Lancaster Linux Users Group is continuing to meet. Their next meeting is August 20th at 7 p.m. You'll have to look online for the details about where that is, or streaming, or whether that's in person. Anyway, and then finally, I'd like to mention the Tech Lancaster calendar to find out about other events that are happening, as well as getting details about a specific event, and that is at techlancaster.com. Additionally, next month, the speaker will be Tyler Philly. I did not have that piece of information directly in front of me, but that should be Tyler Golden, who will be speaking on rebooting the Pirate Box project, which I personally am really looking forward to hearing about. So, moving on. Kicad is it's called an EDA program, which is Electronics Design, probably Assistance. I'm not actually sure what the A stands for. And it is used for typically designing circuit schematics and then circuit boards. So I'll be talking about a little bit about Kicad in general, a little bit about the general process of using Kicad, and then about what the goals are on the project we're going to see how far we can get in designing for this evening. And then from there, we will start into actually going through this stuff. So Kicad is an open source electronics design tool. It has been around for a fairly long time. For a number of years now, it has received a significant amount of funding from the CERN physics laboratories. I would venture to say that broadly its major competitors are Eagle from Autodesk and Altium. I think Altium is the company name. I don't remember off the top of my head. Eagle probably had been the dominant choice for hobbyists until they got bought by Autodesk and taken to a subscription model, which a lot of people hate and has caused a lot of places to start looking at moving their designs over to Kicad. Altium is on the other hand, never been hobbyist friendly. It's a very expensive professional program. It is, I believe, thousands of dollars a year to use. And, I'm sure you get something for that money. I know that there are tools for dealing with high-speed, parallel, differential buses and things of that nature that make life a lot easier that Kicad doesn't have yet, but someday it probably will. And certainly because I know that places that are using it, including CERN, are interested in such things. Kicad, in the meantime, is definitely capable of doing some real work. For instance, the Olimex Terra's laptop which is an ARM-based laptop, was designed, all their circuit boards in Kicad. And then the Great Scott Gadget's HackRF SDR peripheral was done, which involves signals from megahertz to gigahertz on it. And those are just two of the higher profile things I could find real quickly. I believe Olimex does all of their stuff in it these days, not just that one flagship kind of out there project. I should say on a side note, I hear some people say Kicad, some people say Kicad. I go with Kicad. Use what other people around you use, I guess, when you get that. So, the electrical CAD process in general is about making two drawings. The first drawing is the schematic. The major features on the schematic are the symbols, and the purpose of that is for understanding the project. It's kind of more of a high-level, engineer's view, or user's view, or whoever wants to see how the things are connected together. And then the second drawing is the board layout, and the major features on the board layout are generally called footprints. EDA could be done with any vector drawing tool, or depending on how it's going to be manufactured, even a paint tool. Certainly people used to use straight up AutoCAD in the early days when AutoCAD didn't even have that much in the way of seriously technical features to make their drawings for both schematics and board layout. But having a dedicated tool makes things a lot easier, especially in coordinating things between the two different sets of drawings, and it helps prevent mistakes. And we have all sorts of things like design rule checking, which is just one specific way, plus the mistakes of having to copy stuff back and forth between the two drawings. So, if you look at many tutorials, the Kicad process is to first create your symbols. Not real hard, but we're going to be skipping that because everything we want already has symbols available, so why complicate getting started? Then we'll be creating a schematic, and this, by the way, might be an iterative process to try to respect the time. I don't want to put too much in the schematic at first, and then of things that might be nice to include in our Crapduino clone, and then run out of time to actually do the layout. Plus, in the real world you have to iterate, so it wouldn't hurt to show that. So then, after creating your schematic, the next step tends to be creating your footprints for the layout. We'll be skipping that as well because we're going to be getting our footprints from somewhere else. And while creating symbols is relatively easy but a little bit time consuming, creating goods footprints can be more involved, more room for error process. So then the next step in Kicad broadly is to associate the symbols with the footprints. Now this is one place where Kicad tends to be rather different from other EDA programs. In a lot of programs, the two are permanently tied together. So the symbol for a resistor and the symbol for a symbol for a through-hole resistor and a symbol for a SMD resistor are two different symbols, and they are hard associated with their separate respective footprints. Likewise, the symbol for a larger SMD resistor is different from the symbol for a little smaller SMD resistor, again because of the tight association. In Kicad, they are separate. So you so this gives you some flexibility, allegedly, that where you can create a project, and the schematic is good, but now maybe you have to change connectors. Well, you don't have to change the schematic if your connectors all have the same pin out to them, just because they're a different physical form factor. Or maybe you have to change from through-hole to SMD resistors or back, or all sorts of changes can be accommodated by this. Anyway, so that means that there is a step of association symbols to footprints which other systems might not have. Then there is export an intermediate file called a netlist from the schematic to the layout program, import it into the layout program, create the layout, and then things about exporting it for manufacturing at online places. Generally, you produce a package that's a zip file to upload to whoever's going to manufacture it for you. Of course, that's assuming that you're not doing it yourself with a mill or some sort of toner transfer thing, which personally I don't do and never have done. So to recap, it's the steps we're going to be doing will be creating a schematic, creating our symbol footprint associations, creating our and then creating the layout and export. So that gives a fair amount to cover in the next still about 30 some minutes. So let's get straight into it. So what we will be doing, the Arduino. We're going to be making a board that will be supposedly somewhat Arduino compatible, that will be able to run Arduino software. We're going to skip all extras, so it's not going to have a fancy USB port on it, probably. That could be something we double back to, but I have my doubts we'll get to there. It's not going to have a fancy voltage regulator, so you'll have to give it a fairly clean power. Thankfully, USB tends to be close enough. So it's just going to be the bare minimum. And of course, it's not going to have an external clock. So we're going to be using the internal clock feature of the Atmega CPU we'll be using, which is a supported option anyway. So it's not like we're doing something that strange there. So the main type of Arduinos, the Arduino Unos, use a microchip brand Atmega 328 processor. And, excuse me. So I guess the first thing we have to consider is, what does it take to get one of those going? So to that end, this is showing my desktop, which is good, but it is not showing me my head over it. Well, so we're not going to worry about that right now. So anyway, so on the Arduino, they have an Arduino to breadboard guide, which shows you the bare minimum you need to get a Atmega 328 or compatible chip going as a Arduino. So we'll skip down to the minimal circuit, and well, maybe we'll start at the top. So minimally, they say that you need a crystal, a resistor, 2 capacitors, and you can skip some of that if you use the internal clock. So, scrolling down, we can look at how to do that. If you don't have the crystal or capacitors, you can configure to use its internal RC oscillator as the clock instead. that is it. But, you know, I've been giving some thought to this presentation for a while, but I didn't get it all brought together before trying to quickly do it at the last minute for this. This perhaps would be a better document. I will try to remember to include the links in the description or somewhere after I'm done. So the short of it is, this is talking about power regulator. We can skip that. Power filtering. So the basics. Right here is a list of what we need to turn the chip on. Kind of thought there was a crossover in here as well that was needed as well. Well, if this is missing some details, it doesn't really change the point of it. It'll just be embarrassing. So, let's start up Kicad. Let's create our new project. Whoops. We're going to be using an Arduino shield template to get the layout of the board that we want. All right, now so this is what the schematic program looks like. So right here we get some pre-made pin header placement as part of the template, and you know, these connections are all named, so instead of having to drag lines from our chip straight over to here, we just give them the name. Now we're going to need I forget what this one is about. Socket Arduino P5, P8. Well, we're going to ignore that one too, since I don't quite remember what that one's about. Anyway, so the first thing we're going to need is the Atmega 328 chip we're going to use. And this is where one of the reasons that I don't like to insist on people knowing how to make footprints and schematics right away, because there's this service called Snap EDA, which provides you with linked symbols and footprints to many parts, usually to manufacturer specifications. So we look for Atmega 328P, hit enter. They also include 3D models if you want to dive into exporting 3D models of what your board's going to look like. That is not something that I am going to look into. So for this, we could use, I would probably be inclined to use the TQFP here. I just realized once again my desktop is being clipped off, but this time I'm pretty sure I didn't show anything below that was unnecessary. So, or we could use the more popular PDIP. I would often encourage, just go straight for surface mount. Advantage of using the dip in this case is that if we socket it on the board we design, which makes no difference to the schematic or the layout we do, then you can initially program it by popping one out of an Arduino Uno and moving it over to our new board. How to do the initial programming is kind of out of scope. We will be I did say we'll be including something called the ICSP port, which is the official not Arduino, but the official Atmega bootstrapping programming port for their if you're not using Arduino tools. So that's how you would normally download the bootloader to be able to use this. And as long as even if we hooked up a rudimentary serial port to USB adapter here, or break out the TTL serial, which we will do, that's not going to make it be 100% painless programming from the Arduino IDE, because I don't want to get into the final details of that. So anyway, and it doesn't totally matter which we use. I'm just going to pick this one because I feel like it. Download symbol and footprint, pick the version, and boom, it's downloaded. At least initially, that's going to be the only chip I think we're going to be using. So, let's pull this up and open that zip file, and then also pull open my a new window so that I can look at my project location. Hey, buddy. Apparently I'm not doing this for Pirates because there's extra R's in there. So I like to stick the snap EDA files I get straight into the project, check them straight into GitHub. They are, after all, very small. There are other things you could do with them, but I'm not going to bother that. And so I make the snap EDA directory. I create a directory for each part I get from snap EDA, and then copy the contents of the zip file straight over. And then to be able to use those, I do have to add them to the library. Not browse. Where's the library editor one? Manage symbol libraries, project specific libraries, add it. That might not be what I wanted. Yep, sorry. The directory one to just import it this way. Alright. And so now I have that symbol in my project, so I can select the place symbol tool. Can take a moment to take a sip of water anyway. Oh, there, it's done. Here's the symbol I imported, and then I place it. And then, unless we get seriously off into something else, we are I shouldn't actually close that, but hopefully won't use it. I'm going to be done with this for a while. So, the Snap EDA. For parts that the Snap EDA doesn't have, you can get them to make it for from $10 to $20, I believe is the normal price. $50 if you want the full package, including 3D models. And that's for a one-day turnaround, so they'll get you the files in 24 hours. If they already have it, it's just free though, so most things you can just go. The one thing to be alert of is there are some community uploaded. I haven't come over very many, but if it's community uploaded, it could have an error in it. One thing I really impressed me with the company was the one time I did find a community uploaded with an error in it. I reported the error, and in 24 hours they'd made new professionally made packages to replace the community uploaded one. So I was like, hey, I didn't have to pay my $10 or $20. Yeah, you can pay them to get ones that they're missing, and they do it quickly and quickly and accurately. There's all sorts of other libraries out there, free or not, for Kicad to get your symbols. But anyway, moving on. We're at 25 minutes about into this, so we need to keep moving. We should keep that open. Whoops, I don't want to put a new symbol. So, let me make this bigger. And just snapped off the bottom of the screen, I guess. Not really sure where the screen ends, so hopefully that's not missing anything important for people. I don't see any comments about it. And so this is for placing power stuff. This is for placing connections between things. This is for placing buses. We're not going to be covering buses here. I've never actually used the bus in this yet. I haven't done any designs big enough to care for that. This is a no connection flag. Any pins that we don't use on here, we can't just leave them. I mean, we could just leave them connected, but if we do that, then they're going to end up being flagged as errors when we try to use the design rule checks, and that's no fun. So we will be properly labeling them, and then place net labels so that we don't have to actually run the wires all the way. We can just say, run it to A0 out or whatever. So that said, we need the we are also going to need to add a power input of some sort. On the real Arduino Uno, this comes from the USB port or from the 9-volt connector, and they have a power regulator to make that come out nicely. But if we did that, we wouldn't necessarily be crummy enough, so we are just going to put a header at the edge near where the power connectors might go for this. And so in this case, we are going to be looking for a connector I'm making a male one just so it's easier to clip to. It doesn't really matter. And now we have that. Now we are also going to want to add a header for the ICSP. That is traditionally a 2x3 connector. So we will just throw that in here, and we'll move these around later. And notice that, when you add new parts, it doesn't automatically number the parts. So this is U question mark, J question mark, J question mark. We'll have to go through and do that. Now, I also want to add the pin 13 LED that's usually used for the quickly get to blinking thing. So we'll just add a default LED symbol, and we will need a resistor for that. Well, we can move these all around later. So this chip, it has the footprint associated with it from getting it from SnapEDA. These are all generic footprints, so later we will have to associate them ourselves. So then, let's start with naming these. And I will say, sometimes the user interface of Kicad is a bit clunky. This is also true of every other tool out there, but yeah, sometimes I just don't understand why they don't work a little bit more like you would expect every other drawing program to work in certain regards. So anyway, it's the only chip we have, U1. Let's double check over here. These are been named P's, so we don't have to worry about clashing with any of these J's. So this will be edit reference J1, edit reference J2, oops, edit reference R1, edit reference D1 for the LED. We're also going to want to include 2 pins for the TTL serial. So that's going to just be another 1x2 header for now. No, we're going to make that a 6 pin, really? 6 pin header so that it can match more commonly available adapters. And right here is what those 6 pins will be. We might not hook them all up. Alright, so delete this. J3. Now, let's start with the power. No. We really should start with making sure that this is vaguely sensibly placed. I'm just peering over to see which one is the serial pins on the Arduino, and that looks like pins PD0 and PD1. So vaguely up here, so let's move this over somewhere here. You might want to move these across. The ICSP port hooks to PB5, PB4, reset, ground, so PB5, 4, and 3. Oh wait, yeah. So those are PB5, 4, and 3 are over here. So we'll just kind of put this here-ish. The digital output pin 13 on the Arduino is also PB5, so we will leave the resistor, and we will put the resistor and down here, probably make sure I'm only selecting one, something vaguely like that. And we'll just hook the rest of these up to other named nets. Alright, now, power. So, we will go in here and we will add power port and power ground first on the bottom one. And then 5 volts for the top one. And we will drag wires over to that. Alright. So then the LED, we know, connects to ground as well. So we'll throw a ground over here. Oops. And of course the ground pin on the Arduino connects to ground. So we'll throw ground there. And on the serial connector, first pin is ground. So we'll throw ground somewhere up here. And that one we'll probably rotate around just so that it's easier to draw the line for. And I do. So one thing you can't do in Kicad that you can do in most other ones is just click and drag. You have to click to select, then click again to drag. So, drag. Haha. Okay, so we can ignore CTS, DTR on here. I don't know why I'm starting with that. Doesn't make much sense. So let's add the power pin over here. And let's go ahead and just connect this straight up. We'll connect the ground over here, the ground over here. We already connected that one. On the ICSP port, the pin 6 is a ground. Oh, I wish this mat. Well, you know what? I can make it that. No, that didn't. Wait. No, I don't want to rotate it. I want to. I could have sworn there was a flip on here. Alright, here. Alright. That just makes it match the ICSP example that I have open. So, pin 6 on that is a ground as well. I do need to keep hurrying here, so I'm going to try hard to resist making this any prettier. Alright, so on this, we have the ground on top. Check. Pin number 3 is power. Doesn't really matter. We're going to make that one no connect, because it's for power coming from the adapter, not for the adapter usually. We are not going to use the CT. Whoops. I connected that wrong. So we'll delete the wire, delete that wire segment. Okay, CTS, we're not going to connect. RX, DTR, we're not going to connect. So, ground was pin 1. Okay, and then I said that PD0 is receive. Excuse me. So transmit here goes to receive there, and then PD1 is transmit. So that one goes here. Step up, step up. All right, so we're done schematics for the serial port connector. ICSP connector, pin 1 goes to PB4. All right, pin 2 goes to 5 volts. drag the wire for that one. Whoops. Alright, pin 3 goes to PB5. That does not, I don't know, something about that looked funky the way that started. Now, lines that cross, I guess I can't point at the screen easily, so I'll finish drawing this one before I make my comment. Lines that cross like here are inelegant, but they're not a connection. A connection is like that with the dot. Alright, 2 we already did. 1, 2, 3, 4 is going to PB3. And 5 is going to reset. We'll say if we were to correctly rig the serial port, we would be using one of these no connected ones here also to reset, possibly with some sort of support circuitry, so that the Arduino IDE could reset this, and that's what's missing from making the Arduino IDE work nicely with this. Anyway, so that gets us to a good start. I got off track. We have grounds, we have VCC, we have AREF. We still need to do AREF. AREF is not something we really need it here, since we're not going to be using that. But I think, well, you know, it's really something that you should look up in the @Mega data sheet, which is probably this file. And my feeling is that if we're not using AREF, then it should be just the same as VCC. And I'm probably not going to look real hard for this for the sake of time. Conversion range. So you might set it to a different value if you wanted it to convert over a lesser range. Or maybe you can do more. I don't know the fine details. The main point is we're not really using it, but just to leave the option open, we will set that to 5 volts as well. In a non-crappy version, there would be capacitors being used to filter AREF and AVCC here. But, as I said, this is the crappy version of this. Alright, so that should be enough to make the chip run. Then we will get on to the LED. The LED is connected to pin 13. Pin 13, just referring to the printout I made of some of these to make life easier for myself. Pin 13 is PB5 here, so and then that needs to go to a resistor. And I'll put this here, move these down like this, so I'll draw that wire. Alright, note it's saying that time it is a connection instead of just crossing over. There may be a tidier layout to simplify this, but I don't have tons of... I put a photodiode there instead of a regular dot. No, it isn't. No, I put a photo. Why? I put the wrong part there. A photoresistor. Oh boy. All right. conveniently, we can just drag this out, drag this in, boom, delete this, rename this, alright, so that is our blinky LED. Since we're not bothering with a reset switch right now, oh, well, let's just throw in a reset switch. To-do. You know what, no, I'm going back to no switch. We can try that later if there's time. It's not looking like it because I don't have a huge amount of time left. In fact, this is going to be such a crummy Arduino that I don't know how much we're going to get through labeling some of these. So, put a 13 here, make sure that matches. Whoops. Over here. No, they called it 13 SCK. The labels have to match or it's not going to know it's actually a connection. So, zoom back in, scroll to the right, and put that. I don't know what I just clicked. Put that wire in. So we've connected one pin. Now, a whole lot more pins. I'm probably just going to need to go somewhat quickly on these. So we have 13 TV0 is 8. Nope, wrong. Cancel. 8. Is that actually what they called it over here? Let's double check that. Yes, 8. And they called 9 star star. Is star star slash slash SS. PV2 is 10. Yep. And what? We can't put an SS in there? Well, how did they name that way over here? I don't know. Now I may be getting myself into trouble again. Alright. Boy. We didn't even really set up the analog ones correctly. So let's just make those non-connects, which is going to be PC0 through PC5, which is here. Alright, and then ADC6 and ADC7. Not really sure. There should be an X tall in there. Wonder if that's what that was supposed to be. We're going to just click not connect for those. So then find out if that causes it to complain about that. And PD, see, we have PD 2 through 7 to do something with, and those go through to inputs. The input across the top on the connector on the Uno for, again, set likewise 0 to 7. So we'll just do, boy, I almost wish this was just over there. Not sure I really love how they're using the net label in their template. You know what? I'm just going to move that out. Of course, then oh boy. You know what? We're going to limit ourselves to blinking and not connect those two. So, delete this one. Put it placed in the wrong place. I think on here is reasonably connected. Let's perform a check. So it nicely annotates the power where the errors are, connected to other pins but not driven by any pin. Why are they calling that a power input? Now you always have the option of ignoring design rules and electrical rules. That is not a best practice, but you can do it. Sometimes you need to do it because, like, the way the manufacturer specifies that the footprint should be designed, and the way that you get it from Snap EDA or make it yourself to match their specification ends up not to be something that you can make past the rules on that particular part for, like, pins not overlapping or whatever. Anyway, this is not a particularly good reason to skip fixing the problems. And it probably would be interesting to skip at least one of these, but ignoring them won't stop this from working. If there was time, we could come back to do that, but I think we can be pretty safely say there's not going to be time for that. So assign. It tells me that I have to run that for the first time for the new project. We have to wait for it to load. Drink water. Boy, no comments so far. This is quieter than usual. All right. So this is what the assignment looks like. Skip something important here. We do need to, should assign a value to our resistor. So properties, edit properties, value should be Looking at my cheat sheet. 500 ohms. Alright. And we don't have to assign a value to the other one. Anything else right now. So, save that. Go back to assigning footprints. Wait, why is it? Okay, fine. So, oh, I always find this one confusing. Did I rename that off of R1? No. So we can also, the alternate way to assign footprints, which is frankly what I usually do, is to edit the footprint here, and then go straight to selecting. So this was R1, so we just need a regular old resistor and we'll choose a nice 0805. Alright. Now what other ones needed assigned? Come on. Boy, having it ask that every time is going to get old fast. So we need to assign the 3 connectors and the LED. So edit properties, edit footprint. Alright, then we need to do the 3 connectors. Now, all these ones that I'm assigning here are just from the built-in library. I chose a 1x2 there, I believe. And 1mm, no, we don't want 1mm. We are going to want a 2.54mm, aka 1/10 of an inch. Oh, that's why I didn't see it. So we need a 1x2 vertical. Alright, so that's that connector. This will be a 1x6 vertical. And this will be a 2x6 vertical. I don't think I clicked on what I went into there. Properties, edit footprint, select connector, pin header, 2.54. Okay, 2x3. Also vertical. Alright. So I think that if I click on the mapper, it'll show me that everything's mapped. Just to quickly check that. Yes, yes, yes. Alright, no empty spots here. Great. I didn't actually change anything there, so I don't know why I hit that. Generate netlist. Generate netlist. You have to save the net lists. It's whatever they do. And now that takes us to layout. Enable acceleration. Alright, so here we go. We have some markings for spots on here. The pins that cross connect are already in. And so first things first, load netlist. Pick the file we just saved. Close it because I forgot to add the library to this side as well. Since they make the two pieces separate, you have to add the library separate to the two sides. And once again, I don't want that. I want...
now, so we can have donuts.
What, Olivia?
Can we be ready by...
No, not right now.
Oh, what?
Yeah.
It's going to be...
Hey, no.
Donuts. Mommy said we would eat donuts.
Are you all done?
No.
Oh, come here, honey. Sorry.
Hopefully you can wait another 30 minutes or so, sweetie. Yes. Okay, we added the library. We should be able to update now. And there he builds an atlas. Close. So now we have all those pieces. Actually, there's no reason not to just make this much bigger. Try to respect that it doesn't all go in. I know why it's clipping off, because this is not a 1080 monitor, and I've set this to a 1080 string. Alright, so these are rat nested together. That's what these little lines mean. I think then that there's no lines over here. That's because there are no connected ones, probably. So where do we want these things to go? The ICSC one usually goes somewhere in that order. I might not quite have their standard there. The resistor probably goes up somewhere here, because that's about where pin 13 is going to be. This should go in the middle, because it's the start of it. Well, we'll come back to that. The power somewhere over here, just because. LED goes up near this as well. Serial port, well, I remember correctly, it is a serial port more at the top, even though serial port there means the USB serial port, not this one. And then power more at the bottom. So we'll just throw that down there. Alright. Whatever. Now, as you can see, some of these rat's nest lines are crossing each other. That means they're going to have to use both sides of it. The normal thing to do would be to add a big ground fill, which we can do, but let's just start with for power and ground. So add filled zones. Sorry, I guess this is just an interview. So obviously this is footprint all over the place. The layers. So a footprint will have elements that can appear on quite a few different layers. So we have the copper layer, back copper layer, and if you were creating this from scratch instead of importing a template, it might ask you about how to customize these. Adhesive, not really sure what that's used for. Paste is relating to the keep out area for putting for silk screening on solder paste. The silk screen, the mask, all these layers are one of the reasons why I like to get pre-made footprints whenever possible, so you can eliminate having to worry about quite so many of them. So, and it comes down to it, you know, you mostly are going to be using the front and back copper for editing the traces or keypad areas or whatnot, or the silk screen for adding text to this. So, let's try to put this back in better view. I always feel, I can't quite put my finger on it, but I always feel that the zoom and such controls are kind of really weird. So I grabbed the wire tool. I'm just trying to draw in some wires. And the problem here is that the snapping width is not hitting where the line pad is. So we'll just leave that there for a second. So we can set the grid, it's right now set to 1/20th of an inch, but let's set the snap grid to say 1 millimeter. Let's delete this segment, delete this segment, and try that again. So draw. Ha, still not lining up. In which case that probably means that I need to, whoops, position this more nicely, better. Well, it does kind of bug me that these don't want to line up. Anyway, we'll delete that segment. Whoops. No. Well, let's just change that down to 0.5 millimeter, just to try to make this a little easier. Alright, so what I'm hitting into right now is that it thinks that it cares which side of the resistor it hits, which is kind of stupid, but easy to fix by flipping. No, sorry. By rotating twice. There we go. First one done. Alright, don't really care where those are. It would be nice if this was rotated too, really. I think. Well, we'll give it a try. I feel like that looks a little more straightforward. So I don't like this line. Segment. Of course, you can't just right-click on something. You have to click on it to select it, then right-click on it. Come on. Right, fine, we'll delete that segment too. Just start the whole line over again. All right. So as you can see, these light gray lines that represent the rat nest, that's the unconnected wires. As we fill these in, they connect. Now, I don't want to jump straight to doing the grounds and powers yet, because we'll do the power ones, but I don't want to just skip straight to the grounds yet, because we are going to want to that's ground. All right, so to put what we need to do here is place through a via, place the via there, and go around to the back, because otherwise we were going to hit that pin trying to get through here. So as you can see from the color scheme over here, green means that it's on the back copper. I'm just having trouble figuring out where this is trying to point to really for the rat nest. That's why we would refer to the schematic, I guess. Well, let's keep going. So, let's put this pin in. Nope, wrong side. Alright, that's two more down. Place the via. Place another V to go back to the top. And then that's connected. Ground, a ref, STL and SDA share the same pins down here, and we didn't actually hook those up, did we? So that's why they're showing like that. We can come back to them another time. So ground, we're ignoring the grounds, and I'll show you why in a bit. So just go under, whoops. Well, one thing I'd been wondering is if this would be a decent speech for CPOSC, and while I can certainly be faster, I'm not sure How much? Place the via there. Cross things over to here via place and connect. Not sure that I'd be able to trim, say, 30 minutes off of this easily, so I guess it is a good thing I didn't try to do this for the first time there. Alright. Now we need to cross that. I don't know. We're going to have to go under, but can't cross these screens, of course. So this is not going to be particularly well laid out. Make that a via. Sorry, when I say make that a via, I'm also clicking the V key, which is the hotkey for make a via. And going back and forth a lot isn't great, but as I said, I'm just trying to, really blast through it at this point. As you can see, I can sometimes have to kind of wiggle around to try to tug at what it's trying to push towards when it's not what I want. Alright, so we're still on that. I'm just going to come on down here, place the via, and connect. And that one's done. Oops, took me off the wire mode. Drop here, via, place. Wait, was that the ground that I said I was going to? Yes, that was. Drat. Alright, so all of those are done. We still need to do these down here. That's grounds, 5 volts. I'll just click it there, I don't care. Ground, those cross connect ones, ground, whatever, we'll come back to that. So, add filled zones. We are going to make a filled zone of ground on the back. We're going to It may seem we're including all sorts of non-ground things here, and if it seems that way, though, we are. Alright, so that is our ground. Now, you can see it trims out anywhere that there's things going through it for us automatically. Yay! So now what is not connected? We probably need to force a redraw. Oh, we put that on the back. Maybe not the best decision in retrospect, but we did it. So we still have to run vias to the back for things. So that takes care of that one. The actual through holes over here are taken care of because they already go to the back. Why was this not taken care of? Okay, this is not taken care of because we still have to add Alright, so that connects those ground pins. And so alright, we still have to connect this to the actual Crapduino, where it happens to connect to that pin there. Alright, so we still have a problem with these two pins, which are cross-connected across the board, but we're not actually using them, which I suspect means that when we do a design rule check, we're going to get two... What? We're going to get... They're going to show up as unconnected, but we have no other design rules. So in theory, we should have a design, even though we have two design rules. Again, design rules shouldn't be ignored, but I'm already 20 minutes over time, so I'm doing that. Now, we would probably also want to add a label for this. Something like this. And then we can sort of call it done-ish. I mean, this is something that you should be able to make. You should be able to use the ICSP to program it and have the lights blink and use the few pins we connected up. We did a lot of not connects to try to fit this in time-wise. Did not go as expected. Anyway, so then, bizarrely, I think, you use the plot, to export it. So you are need to select an output directory. Let's just call that Gerber for now. Oops, I guess we need to create that. So we'll select this folder. Hit plot. That creates the front copper, back copper, front silkscreen, back silkscreen, generate drill files. This file tells the manufacturer where to drill holes through that will then be plated. And usually pretty much all the defaults work there too. Generate that. Generate map file. Don't know if we really care, but we'll do it. Generate report. Sure, why not? And so then we go back to our file browser, go into that directory. We have this, which is something we should be able to upload to a manufacturer as a zip file to have this manufactured. I'd say any questions, but it looks like at this point I'm the only person watching myself. Maybe this will pick up more watches later. Anyway, have a good evening. Remember to sign up for the Slack channel by going to amishtech.slack.com or check out the calendar at Tech Lancaster, and we'll see you next month. Have a good evening.